Okay, let's dive right into this. If you've ever stared at a custom circuit board and wondered exactly how the main brain talks to all its sensors, memory chips, and displays so flawlessly, well, you're in the right place. Today we're mastering the serial peripheral interface, or as we all know and love it, SPI. Think of SPI as a highly disciplined, incredibly fast conversation. It's a full duplex exchange that is perfectly orchestrated by a master controller. And honestly, understanding this synchronized conversation is going to unlock a massive part of embedded development for you.
So here's our roadmap for this explainer. 1. Anatomy of the SPI bus. 2. The rules of communication. 3. Hardware and network topologies. 4. Software drivers and optimization. And finally, number 5. Bringing it all together. We're going to build our understanding from the physical wires all the way up to advanced software optimization and debugging.
Let's kick things off with Section 1, Anatomy of the SPI bus, the physical signals.
To really grasp what makes SPI tick, I want you to imagine a symphony orchestra. You've got a central conductor, which is our master controller, and various instruments representing our peripherals. To keep them all playing in perfect seamless harmony, they use a full duplex setup. So the crucial point is that SPI isn't a walkie-talkie scenario where one side speaks, pauses, and then waits for the other to respond. No way, it's a simultaneous exchange. Every single time that clock ticks, one bit of data gets shifted out of the master, and at the exact same fraction of a second, one bit is shifted into the master from the peripheral.
Now, to handle this two-way traffic without a crash, we use two dedicated lanes. We have MOSI, master out, slave in, and MISO, master in, slave out. Two completely separate lanes for data. And notice here that the controller alone drives the show. It generates the serial clock, or SCK, which dictates the speed of the whole operation. And it alone commands the chip select, or CS, which basically taps a specific peripheral on the shoulder to say, hey, wake up and listen to me.
Which brings us to Section 2, the rules of communication, timing and framing.
Because this conversation is happening at absolutely blazing speeds over physical wires, both sides must agree on strict timing rules before anyone utters a single digital word. Understanding these 4 classic SPI modes will literally save you hours of debugging down the line. The modes depend on 2 master settings. First, clock polarity, or C-pole, which sets whether the idle clock line rests at a low or a high voltage. Second, clock phase, or CPHA, which decides whether data is sampled on the first edge or the second edge. A mismatch here is hands down the most common trap for developers. If you get this wrong, your bytes are going to be shifted, corrupted, or just read as complete and utter garbage.
But once those modes match, we can actually start talking. The flow of a standard transfer is highly rhythmic. Step 1. The master asserts the chip select line low, singling out the peripheral. Step 2. The master sends a command byte or an address. Step 3. The master continues to clock data, either sending a payload or pulling in a response. And Step 4. The master deasserts the chip select line high, cleanly ending the transaction. Tick, 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 tick. It is a perfectly synchronized data frame.
But wait, let's pause here for a second. This is a bit of a mystery. If only the controller is allowed to generate the clock signal, how on earth can a peripheral send data back during that read phase? I mean, the peripheral can't just start talking on its own, right? It literally has no clock to drive its own bits.
Well, the answer is dummy bytes. Think of it like being on a phone call. If you want the other person to keep talking, you have to occasionally say, aha, or yeah, just to keep the conversation flowing. It's the exact same concept in SPI. The controller sends meaningless data, often hex 00 or FF, simply to force the clock line to tick. Those ticks give the peripheral the physical mechanism it desperately needs to shift its actual valuable data back to the master on the MISO line.
And this brilliantly illustrates the most fundamental mindset shift you need when working with SPI. Reading still requires transmitting, because clocks only come from the controller. Every single frame on the bus, even if you're just asking a simple sensor for its temperature, is inherently both a transmit and a receive operation from the perspective of the SPI hardware.
Okay, moving to Section 3, Hardware and Network Topologies, Wiring Multiple Devices.
So we know how one-on-one conversations work, but as we mentioned earlier, our conductor usually has a whole orchestra of chips to manage. In a standard multi-device topology, the clock, MOSI, and MISO lines are shared across all peripherals, like a bus. But each peripheral gets its own unique chip select line. When the active load chip select isolates one device, the others basically disconnect themselves, ignoring the bus. But then we have the daisy chain topology, which is super fascinating. Here, all devices share a single chip select line, but the data physically cascades. The MOSI goes into the first device, the MISO from the first goes into the second, and so on. The bits literally shift through a line of peripherals in sequence.
Let's move to and see how this builds into the next layer. Section 4. Software drivers and optimization.
All right, we've conquered the electrical wiring. Now let's talk about the software that actually drives the whole shebang. A robust software architecture separates things out into 3 key layers. First, the bus layer, which handles the pure hardware details, speed, mode, and bit order. Second, the device layer. And this is absolutely crucial because SPI support on a microcontroller really only gives you the shifting engine. The actual protocol, the specific commands, the dummy bytes, the registers, that's all defined by your specific peripherals datasheet. And finally, you have the application layer, which gives you those clean, usable APIs. Separating these layers keeps your code super clean and makes debugging infinitely easier.
Now, when it comes to high throughput, you can't just rely on the CPU to slowly shift 1 byte at a time. That's a huge bottleneck. You have to progress through hardware acceleration. Usually start with basic polling for simple reads and early bring-up. Then you move to interrupts for moderate asynchronous traffic. But when you need to drive a high-res display or sample high-rate ADCs, you've got to shift into high gear using FIFOs and direct memory access, or DMA. DMA allows sustained, massive transfers with almost zero CPU load, literally blasting data across the bus at maximum speed.
And that brings us to our final part, Section 5, bringing it all together, troubleshooting and best practices.
This right here is the insider knowledge. These are the exact traps that catch every single embedded developer during a new board bring-up. When a new SPI device doesn't work, do not panic. Start with the basics. Confirm your power, ground, and logic levels. Verify your chip select actually goes active and only selects one device at a time. Double-check your SPI mode and clock speed against the datasheet. And pro tip, always start with a slow clock. Try to read a known static register, like a device ID. And finally, always inspect the traffic with a logic analyzer before you start tearing your C code apart.
Now, what's really interesting about these failure patterns is that the specific hexadecimal values actually translate directly to physical fixes. If you're reading all FFs, you likely have a floating MISO line, the wrong chip select, or the peripheral just isn't powered on to drive the output. If you read all 00, well, check your power state, look for a held reset pin, or honestly just bad wiring. If your bits are shifted by just one position, yep, you have that CPHA or CPOL mode mismatch we talked about earlier. And if the very first transfer passes, but later ones fail, you're probably looking at a startup delay issue or a stale FIFO buffer.
Which leaves us with this final kind of provocative thought. If SPI is really just about shifting bits synchronously across 4 wires, why is your specific device driver the actual missing piece of the puzzle? Well, the answer is that SPI itself is just a blank canvas. It is a remarkably fast, elegant electrical standard, but it enforces no universal language. To truly unlock the hardware, you must dive into your specific peripherals datasheet to learn its unique dialect. Thank you so much for joining me on this explainer. Keep learning, keep building, and I will see you next time.